Hey guys, so today will be our second to last video on the course. That's awesome. And we're going to talk mostly about hyperbolas, but I wanted to finish off ellipses. I didn't actually give you a definition for that. And I know not everybody's going on to um, maybe post-secondary where you're going to be studying math or maybe physics or engineering, but some of you are, and I think it would be only appropriate that I give you that. So, for some of you, once again, it's not super important, but here we go. So we look at the definition here. So the definition of an ellipse, this is the ellipse right now, just finishing that off. It's kind of a weird definition. So it's the locus or set of all points in a plane where the sum, see, not sum, but sum of the focal radii is a constant. So what that means, if you draw an ellipse, I'll use it draws a bit better for me. There we go. So there's our ellipse. And if you look at the major axis, which is always along the longest dimensions of the ellipse, there's the major axis. We said you have your center there, and you have a focus here, called focus 1, and a focus 2. So this says that any point on the ellipse will have the same focal radii sum. So what does that mean? Well, let's put a point on the ellipse here. We'll call this point P1, okay? And if you measure P1, F1, and you add that to P1, F2, that is equal to a constant value. And once again, if you made it point maybe way over here, let's call this point P2, and you measure this distance and you add it to that distance, so this would be P2 F1 plus P2 F2, that actually equals the same constant. So the sum of the focal radii. So in a circle, you have just a radius, but depending where you put your point, you'd have two radii coming from the focus. So this number is always a constant, and that number actually always equals 2a. Always equals 2a. And if you check the book, they actually do define this for you. So if you're not too sure what I'm babbling about, it does show you a formula in there how you can actually calculate out that value. But I'm not holding you accountable to that. But I think you should know that if you're going into, you should know the definition, sorry, if you're going into certain areas of math and physics and engineering. Okay, so what also is 2a though? Well, the major axis of an ellipse equals 2a. And remember, the minor axis equaled 2b. Okay, so those are some things you need to know about ellipses. So really the major axis is the sum of the focal radii. It is this constant number that never changes for ellipses. Okay, so I just wanted to finish off ellipses there and move on to hyperbolas now. And hyperbolas, I would say, are probably the most complicated formula and sort of properties of all the conic shapes. And because of the time we are in the course and the nature in which we're teaching you, I'm going to probably be removing a lot of the more what I would call complicated parts of the unit. So I hope that helps a bit. But just covering the basics of that. So I'm going to start with the definition of a hyperbola here. So let's start with the definition first. It's usually where I should start these things off. So really the hyperbola is the locus. So the locus, or the set of all points, locus of all points, set of all points in a plane where the difference, the absolute difference, the difference of the focal radii is a constant. So kind of like the ellipse definition, except for now it's looking at difference. And so I'm going to draw you a basic hyperbola and then just kind of show you what this definition means in the first place. So the hyperbola looks kind of like two parabolas. We see that maybe an arm looks kind of like that. And another arm looks kind of like that. And I'm just drawing these freehand, so this may not actually meet the definition if I draw this accurately here. But kind of in the mouth of the ellipse, in the mouth of the hyperbola, very much like a parabola, you have this focus. We'll call that F1. And over in the far side, you have another focus. So you actually have two foci for a hyperbola. A parabola has one focus, an ellipse has two foci, and the hyperbola has two foci. And so what this is saying is if you take any point you want on the hyperbola, it doesn't even matter which arm you look at. Let's take a look at this point right here, point P1, and you measure that distance. And then you measure the distance from that point to the other focus. And you took the difference of those numbers. It doesn't matter how you do it. It's actually the absolute distance. So let's say P1, P1 F2, and you minus the distance from P1 F1, that would equal a constant. And so once again, if you were to pick a different point, like say you picked a point over here, P2, then the distance here, if you measured that, if you took the absolute distance, a difference between the distances, sorry, P2F2 minus P2F1, I guess that would have been a 1 up there, and you take the absolute value of that, you also get the same constant. So it doesn't matter how you measure it, that's going to always be true for a hyperbola. And just like the ellipse, it actually equals 2a. So it equals 2a. Now, in this kind of picture, the a is a different meaning than it does in ellipses, though. So there's no major axis in a hyperbola. Okay, so let's talk about some of the formulas we're going to work with here. So once again, I'm kind of jumping over a lot of the how these formulas are created. And so if you really are interested in learning about that, it does do a fairly good job in the book of going through all the formulas, but it's quite a slug to get through. So I'm kind of trying to reduce this down a bit for people so it's a bit more manageable. So x minus h all squared. So we've seen things like that before. And now we do minus y minus k all squared over, and then equals 1. And then you can also have y minus k all squared minus x minus h all squared equals 1. And these are over things. And now you might think back to the ellipse formula, which is very similar to the ellipse formula, except for with ellipses, you're adding them just like you are in circles. With hyperbolas, you're subtracting them. And now below the positive term, in this case here, the x's, you get a squared. And below the negative term, you get y squared. So this would be a squared, and this would be b squared. Now, here's the part we need to be careful about, is that in the ellipse, the longer axis, the major axis, was always the a value, and the shorter axis was always the minor axis, which was the b values. That's how they kind of related them. And so with hyperbolas, it has nothing to do with how big or small the number is. It has to do with which term is positive. So we'll give you some examples in a second here, but you want to make sure you don't get that confused because it can easily make you draw the wrong picture. So whichever term is positive, so for example, in our equation here, this term is assumed to have a plus sign here. And so the number under that is going to have something to do with this a value being squared. And the y term is the negative number. And so the b squared goes underneath that one. Okay, so that's something we want to make sure a distinction we understand between the two of them. Okay, now what do you think h and k tell us though? Like what do you think h and k tell us? So in the circles, it was the center. In the ellipses, it was the center. Now, admittedly, in the parabola, it was actually the vertex, but in the hyperbola, it's also the center. So the center of a hyperbola will always be at h, comma, k here. Now, if the hyperbola has a positive x value, a positive x squared term, then when we draw it, it's going to open left and right, like the one I just drew above. Okay, so I'm just going to redraw a new picture here. I'm going to put in some of our other letters here. So the hyperbola might look like this. Now, of course, it can be moved left and right, just like any function can be. Actually, it's not a function. It can be moved left and right, like any relationship can be moved. But it kind of looks like I'm centering at 0, 0 here. So this graph would have an h value of 0 and a k value of 0, but you can move it wherever you want to. Okay, so just some terminology here. So let's make sure I give you the right definitions here. So the first thing is we have what we call the transverse axes. So the transverse axis is the axis that runs between the two vertices of the hyperbola. So let me just draw that in for you guys. So the distance from here to here, that is the transverse axis. And I'm going to abbreviate that TA. So TA, the transverse axis, is always equal to 2a. So it's actually the difference of the focal radii. It actually gives you the same value. And once again, the book shows you that if you're curious. And then there's this kind of pretend axis, which sounds silly in math, but it might make more sense when we draw this thing, which goes up and down. And this is referred to as the conjugate axis. Now, I'll need to talk a little bit more about that later because it doesn't make sense really right now why we would have these arbitrary points on the line. And I'm going to call that the CA. Okay, so CA. And the conjugate axis, as you might probably predict it, is equal to 2B. So the distance from here is B, from the center. Let's put the center in. Center is at 0, 0 here. So B is the distance from the center to the end of the conjugate axis, and also from the center to the other end of the conjugate axis. And the value of A is the distance from the center to the vertices, and from the center to the other vertices here. So that would be A. So the transverse axis is 2A, and the conjugate axis is 2B. And let's take a look now. So we have, oh yeah, and also the foci, I should have mentioned that. The focus here, and the focus over here. The distance from the focus to the center, it's gonna be hard to draw this in here, a lot of stuff here. Let me choose a different color. Let me use all my colors up here. Let's just choose purple. There we go, purple. Okay. The distance from the center to the focus is C. And from the focus to the center is C. So we have all these different things here. And then the formula that kind of relates A, B, and C is actually the Pythagorean formula. So A squared plus B squared equals C squared. And once again, I'm not deriving that for you. You just kind of have to take it on faith that that's true. But remember, the ellipse formula was different. It was actually a squared equaled b squared plus c squared. So make sure you, if you're doing your test, make sure you write that down somewhere so you know the difference between the two of them. And then for the other picture, if you were to draw a parabola, or sorry, hyperbola where the y's are positive, then what you would notice is that it actually opens up and down. And so what you would see is maybe you have your vertices here and here, and opens like this, kind of like that. And the other one would open downwards. Boy, that's really bad. Okay. Oh boy. There we go. Okay, so there's our hyperbola. And then of course our center would be here. And our distance A is the distances from the vertices to the center would be A, and that would be A. And what you'll notice now is that the transverse axis is the other way now. So this is why we say that the A squared term is under the positive term. So this axis from here to here, this would be the transverse axes. And then you'd have this arbitrary axis, which I haven't really explained very well, called the conjugate axes. And so that would be the distance from here to there, and that's going to be B and B. So this is the conjugate axes. And then you would have foci that would be in this area and this area. Okay, and that the distance from the center to the foci would be C. And once again, they would be related by this formula. So what you have to get your head around is the idea, how do these things open? So if it's a positive X term, then it opens left and right. If it's a positive Y term, it opens up and down. And so you kind of have to be able to distinguish that. So let's take a look at just some information here. Let's write a hyperbola here. So let's make this 16. Okay, so I'd like you to write down what you think, or where you think the center would be. How long do you think the transverse axis is? And how long do you think the conjugate axis is here? Okay. Okay, so I need some variables here. So I need to know H, I need to know K, I need to know A, and I need to know my B values. So many of the questions, you're probably getting a sense now that it's really just sort of determining some letters. And once you know the values of those letters, you can kind of predict anything about the shape here. So I have to remember that the H value is with the X. So my H value would be this thing here. So that's got to be related to the H. And my K value has to be that one. Now, normally it's X minus H. So the H value must be -3. And the K value now must be +2. So now I know where my center is. My center must be -3 and 2. My transverse axes, now I got to be careful here not to confuse this with major and minor axes, because if I was looking at an ellipse, I'd be looking for the bigger number for the major. But to get the A value, I need to be looking at the term that's positive here. So my Y value is positive, which means that A squared is equal to 16. Which means the A value would be equal to 4. And then my B value would be equal to, related, sorry, to the term that's negative, which is the X term. So I need to look at the B squared value being 25, which means my B value is 5 here. Okay, so how long is my transverse axis? Well, the transverse axis is always equal to 2A. So 2 times 4 would be 8. And the conjugate axis is always equal to 2b. So the conjugate axis would be 10. And you can notice here that the conjugate axis is actually longer than the transverse axis, and that's okay. That's not a problem. It has to be so it has to do more with which term is positive and which term is negative here. So I'm gonna keep going with this question. and try to show you where this whole conjugate axis is used, like why we use the conjugate axis here. And I'm hoping I can do it well on this my tablet here. But we're going to work with the same equation. So we're going to work with this this formula here. Let me just put a box around it. Okay. So we're going to work with this equation. And when we draw that, we are going to try to make sense of all these numbers now. Okay. So let's scroll down here. Hopefully I'll be able to fit this on. I have a student who I taught a long time ago, and don't think he's well. Okay, so here we go. He's emailing me a lot. It's kind of creepy, actually. Okay, so here we go. So don't be creepy, okay, guys. Here we go. So let's take a look at our picture here. So where's our center? -3 and 2. So there's our picture there. Okay. Now center is -3 and 2. So now I'm going to try to find my vertices. So that has to do with the transverse axes, but I have to understand that this thing either opens left or right, or it opens up and down. So I have to go back to the equation now, and maybe I'll write my equation down here so I can kind of don't have to keep scrolling up. So y minus 2 all squared over 16 minus x plus 3 all squared over 25 is equal to 1. Okay, so let's move up there. Okay, now this thing has to open up and down because the y values are the positive terms here. So what I'm going to do is go up 4. So 1, 2, 3, 4. And I'm going to place a point here. And I'm going to use a different color here because the center is actually not a point I'm going to draw in the real picture. And then, so this was 2, and I have to go up 4, so that makes that 6. And then I have to go down 4, so 1, 2, 3, 4, and I'm going to put a point here. So you can see between the two vertices, that's a distance of 8. There's 8 units between there. So that is the transverse axes. So how do you draw this thing properly now? Like how do you know not to do it like or like really wide kind of thing? And that's actually where the conjugate axis comes into play now. Okay. Now these functions actually have, so these relationships actually have asymptotes. So let's take a look here. So how does this work? So we're going to get you to draw what's called the box, or I call it the box. Actually, it's a bad word to call it the box. My student said to me last year, because it's not a box, it's actually a rectangle. A box is a 3-dimensional shape. I thought, yeah, I guess you're right about that. So I'm going to call it the rectangle now, okay? So I'm changing my tune here. So my conjugate axis is 10 units long, which means the distance from the center to the end of the conjugate axis is 5. So I'm going to move over 1, 2, 3, 4, 5. That's -3. That would be 2. And I'm going to put a black dot here. It's not part of the function. Okay. So the blue is going to be the actual graph when I draw it. And I'm going to put 5 units this way. 1, 2, 3, 4, 5. So that's going to be -8. And put a black dot there. And now what I'm going to do is I'm going to create a box. I'm going to use a sort of a dash line here because it's not really the function. And if you notice, what I'm creating here is a rectangular shape that has the dimensions of the conjugate and transverse axes. So that is that it's the distance from top to bottom is 10, sorry, is 8, and the distance from left to right is 10 here. And now what's going to be true here is if you use a ruler and you do the diagonals of this box, they'll pass through the center. And now I want to draw, these are going to be asymptotes. So these are not places the graph's ever going to reach. So remember when we did log functions or exponential functions, we used a dash line for this. So I'm going to go dash line here. Okay, and I flip my ruler and I draw the diagonals of this box. Of this rectangle. It's not a box, Mr. Dixon. Okay, so there are 4 lights. Okay, so here we go. So there's our diagonals here. Okay, I'll get rid of my ruler. And now what I want to do is go back to the center. Can I remember our center up here? And what I'm going to do my best here is I'm going to draw a hyperbola that approaches the asymptote. So I'm going to approach this asymptote. Okay. Approaching. Yeah, no, it will never cross this line, these lines. And that's a pretty wide hyperbola here, okay? So that's our hyperbola here. So now, next thing you'll be asked is what is the equation or what is the slope of the asymptotes? And I want to show you how to do that relatively quick here. I'm just going to pause my video for just 1 second though. You probably won't even realize this. Okay, there we go, guys. So, so we're going to try to find the equation of these asymptotes, and you'll have to remember there was an equation we gave you in the first video of this unit. We talked about another way to write the equation of a line, and I'm going to use that equation. It's derived from the slope definition, and so that formula is. Let me just go over here. So we know that slope is y2 minus y1 over top of x2 minus x1. And the equation I did is I brought the x part over to the to the left-hand side, and now we get y2 minus y1. Okay, so the question is, well, how would we use the information on the picture here to do that? Well, the first thing you're going to do is you're going to want to find the slope of the lines. And I'm going to solve this just for one of the lines, but you can see how easy it'll be once you know the other slope here. So let's pick the line that has the positive slope. So I'll call this one the first asymptote there. Okay. So what would the slope of that line be? Okay. Well, what I would do is I would go to the center, and I would do like rise over run and figure out how far you went up here. Okay. And if you look at the graph, your rise would have been 4 units up, and then 5 units that way. So you would have gone 4 up and 5 over. So the slope would be 4/5. And of course, the other one would just be negative 4/5 because you're going downwards. Okay, so I would just say it's 4/5 goes up down. Sorry, up 4 over 5. So let's put 4/5 in here. So 4/5 into the equation. And so now what you need is you need to have some other point that's on that line. Now notice we're not talking about the hyperbola here. We're talking about the asymptotes. Okay. So the asymptotes, notice that they all go through the center, and you knew that, like you knew where the center was. So let's use those points now. Let's use those points as a place that both lines will go through. So that would be -3 for the x value and a 2 for the y value. So that's where the center is. And I'm going to plug those numbers into this equation for finding out the equation of a line. So I go x minus. Now I got to go minus -3, so really +3. Okay, and that equals y minus 2. Okay, now 4/5 x plus 3 equals y minus 2. Now you could leave it like that. I wouldn't mark you wrong if you stop there, because that is the equation of that line. But maybe as a student who wants to graph this kind of line, you might find that tricky to know how to graph. But now that you know the tricks, you might not find it tricky. That sounded totally backwards. But for example, like I know from looking at this graph, I know that the line goes through -3 and +2. So I could just put a point there, and then I could just do the slope from that point if I wanted to. But if you wanted to put it into y equals mx plus b format, which some of you may prefer, well, then just do a little bit of distribution here. So you would distribute the 4 over 5 in. So you get 4 over 5x plus 12 over 5, because 4 over 5 times 3 would be 12 over 5, equaling y minus 2. And now bring the 2 over. So I would get y is equal to 4/5 x. And then I have to do 12 over 5 plus 2, which is really 10 over 5. So I'm 22 over 5. So once again, pretty ugly y-intercept here, but you could write it in that format, or if you just left it in that format, that's also fine. Okay, I kind of prefer this because it's just easier to stop there at that point. No fractional math here. Okay, so now let's sort of pick this apart here. And I said, remember, I said this is a hard little unit. I'm trying to make it easy here, but it's already seeming like some kind of epic question. So y minus 2 all over 16, we said, minus x plus 3 all over 25 equals 1. Okay, so there's what we were given. That's how we started the whole problem started this way. It was a big problem. Life's a problem. Okay, so how could we do that? So if we're trying to go from, let's say we're trying to go from here to there, right? We're trying to go from there to there. Well, notice that you actually have almost everything already in the equation. It's already, sorry, that should be squared there. You basically have all those things right there. So if the slope formula is x2 minus x1 times m, well, look at that x plus 3. That's already right there. You have it right there. And then y minus 2, there it is right there, y minus 2. So you already have that part. So you didn't even have to draw the picture. If you're just asked to write the equation, you could just say, well, that's my x part, that's my y part. Now, I guess the bigger question is, how would you get the 4 over 5, do you think? Just looking at this, if you didn't have a graph, how could you just look at that equation and get 4 over 5? Well, if you notice the square roots of the two bottom numbers, the square root of 16 is 4, and the square root of 25 is 5. Now, I'm going to deviate from the book here. The book actually gives equations, different formulas, depending on how the hyperbola opens. But I want to show you a little trick that will avoid you having to memorize different formulas for the slope here. And what I'm going to go back to is that slope is rise over run. So y is the rise, right? So y is always the rise, and x is always the run. So what I do is I just take the number that's underneath whatever the y term is, and I square root it. That gives me 4. And then I take whatever number is under the x term, and I square root that, and that gives me 5. And then I just remember slope is rise over run. So that would equal 5. Sorry, I shouldn't be talking and thinking at the same time. My rise is 4, and my run is 5. Now, there is another asymptote here. This would just be one of the asymptotes. So let's find the other asymptote, and I'm going to completely cover the graph up now, right? I'm going to completely cover the graph up and sort of show you what I mean by using this formula we talked about early on. So we know that m times x2 minus x1 equals y2 minus y1. We know that's the equation for a line, at least another way to write it. So let's say I'm looking at this equation here, and I'm thinking, well, I already have the positive slope line. Let's find the negative slope line. So all I do is I square root the number under the y, which is 4. And I square root the number under the x, which would be 5. And now it's just a negative slope. And now I need an x component, but I know that it's going to be x plus 3, because the center would be at negative 3. So one of the points would be at negative 3. And the y part would just be y minus 2. And I'm done. And so I didn't need a graph, didn't need to do anything crazy there. So let me give you one more question of this type and see if you guys could do that on your own. Okay, see if you could do that on your own. So let's say you had the equation x plus 2 squared minus y minus 3 squared equals 1. Let's make this over 9, and let's make this over 64. Okay, and so what I want you to do here is write the two, write the equation for the two asymptotes for this hyperbola. Okay, well, I know the equation formula for a line can be written this way. It's just another way of writing it. And I know the center for this hyperbola would be -2 and 3. But I could just plug those in right now and just say that's going to be x plus 2. That would be one of the points it would go through. And it would go through y minus 3. Okay. And in the slope part, I just look at my rise and run. So I know that the y part is 9, underneath is 9, And I know underneath the x part is 64, so I'm going to square root both those numbers. So my rise has to go rise and then overrun. So it has to be 3 over 8. And I guess there'd be a negative slope one, so negative 3 over 8, x plus 2, y minus 3. And notice I didn't graph anything. I just kind of sketched it. Sorry, I didn't graph anything or sketch it. I just sort of looked at the equation and based it on those things. So how do you think this would open though? Do you think it'd be left or right? And what do you think the major and minor axis would be? Why don't you guys figure that out? Major and minor axis. Okay, well, it's got a positive x term, so it's got to open left and right, so it has to open left and right. Well, I said major and minor, I should say transverse axes. Transverse axes, conjugate axes. The transverse axis is always dealing with the positive term. So the positive one is 64, sorry, is the x term, so that's 64. Square root of 64 is 8, so that would be a is equal to 8, right? And so we have to double that, so that would be 2 times 8, which is 16. Okay, and then the conjugate axis, that's b squared value is 9, so the b value would have to be 3. So we have 2 times 3, which would be 6 then. So the conjugate axis is 6. And our last question, which is a little tricky, is the focus. What would the coordinates of the focus be? Where would our, actually foci in this case here. So let's find out the coordinates of the foci. Okay. So first of all, I kind of have to get an idea how this thing's oriented first. So it's going to look, as we said, actually, I don't even need the crosshairs. Let's just draw the hyperbola like this. Okay. So I know it opens that way, and I know the transverse axis would run like that. Okay, that's what the transverse axis is, and that's actually 16 units long. But I'm just going to extend it through. So this is not really the transverse. It's just the line that the transverse axis would be on. And what I now know is the foci has to be on these, or on that line, but inside the actual kind of mouth of the hyperbola. So it kind of opens like this. It has to be inside there. And I know the distance c is from the center to there, okay? And c is from the center to here. But what I should notice is the center here is at -2 and 3. And notice that each foci would actually be at the same height as the center would be. So I know for one of the values, it has to be a 3 on the end. And for the other foci, it also has to be a 3 on the end. And so the question really is, what is the x value that you would be at here? And what you'd have to do is start at -2 and move c units to the left and to the right. So let's just use our formula for that then. So we know that a squared plus b squared equals c squared for the hyperbola, not for the ellipse, for the hyperbola. And what was my a squared value? Well, that was the number under the positive term, so that's 64. And my b squared value was under the y term, so that's 9. So I know that c squared would be 64 plus 9, which is 73, which is kind of an unfortunate number, but still works. So c would equal plus or minus the root of 73, and that is not a perfect square. So I would have to start at -2, and I'd have to go to the left root 73. And then I start at -2, and then I would go to the right 73. So it's kind of a tricky one there. I think I'm almost done. What I wanted to do was one more question. I know it's maybe a bit longer video than I had hoped, but you have to trust me. I'm really trying to shorten it for you here. There's a lot of other weird stuff going on. So let's take a look at one last question. And that has to do with getting a hyperbola in general form and then turning it into standard form and answering some questions about it. So let's say you had y squared minus 4x squared plus 6y plus 32x minus 59. And all of that equals 0. And they ask you like questions maybe like, where's the center? How long is the transverse and conjugate axes? What's the slope of the asymptotes? There's so many questions that could be asked here that I think would be pretty much impossible to answer in the way it's written. It's very complicated to figure it out. I would even say asking questions like, how does it open? that actually could be tricky too, because if you start bringing numbers to the right-hand side and they become negative, and at some point you have to divide by a negative, then you're going to switch the signs of all the other numbers. So like right now, my brain is saying, oh, I think it opens up and down because the y is positive, the y squared is positive, but I don't know if that's going to be true once I start moving things around in the equation. So you want to be really careful about making predictions about what this thing looks like if you don't have it in the standard form way of writing it, which is what we wrote up here. So this is our standard form, okay? So you want to probably convert to that first before you make any kind of guesses as to what's going on here with this. So what I'm going to do is just complete the square as I would normally. And I'm going to group my y terms together first because they're kind of in the beginning. And I leave a space to complete the square. And then I go negative 4x squared. And then I'm going to, where are we here? Plus 32x. And then I'm going to make this equal to 59. Now I need to do a little bit more organizing here because this negative 4 is a bit of a problem. I'm going to write y squared plus 6y plus a number, and I think most of you guys know what that number is, but let's just keep the suspense going. I'm going to divide by negative 4, or factor negative 4 here, which makes this x squared, and then instead of being plus 32, it's actually going to be minus, that was an x there, minus 8x plus a number equals 59, and then I have to add a number and then add another number, okay? So I'm just making sure we're okay with that part. All right, so what are the numbers here? Well, take 6 divided by 2 and square, it gives me a 9. And so I just added 9 to the left, so I'm gonna have to add 9 to the right-hand side. And now I take negative 8 and divide it by 2 is negative 4. I square that, that gives me 16. Now I gotta be careful here. I don't wanna write 16 on the other side because I didn't actually add 16 because that 16 is being multiplied by the negative 4 in front. So you actually do it by putting a 16 there, you actually subtracted 64 from that side. So I need to subtract 64 from this side, okay? So remember I was mentioning about the right-hand side maybe being negative. You gotta be careful about what pops out on the other side here. It may not be negative. In fact, I don't think it is, but just be careful about that. So now I'm gonna complete the square. So y plus 3 squared minus 4 x minus 4 squared equals, and now I have 59 plus 9 minus 64. So I get 4. Okay, so it's looking better. It's looking, I can sort of tell where the center is now. But what I need to make sure is the right-hand side equals 1, just like with the ellipses. So I'm going to divide everything by 4 here. So I get y plus 3 all squared over 4 minus, now the 4's would cancel, so x minus 4 squared equals 1. So now I need to find h, I need to find k, I need to find a, and I need to find b. Alrighty. So my h value is 4. My k value is negative 3. My a squared value is 4, which means, because remember a is the one under the positive term, not the bigger one, but the positive term. So a itself would be 2. And underneath the negative term is the b squared value, which have to be 1 here in that case. So where's the center? The center would be at 4 comma negative 3. Where is the what's the length of the transverse axes? The transverse axes here would be 2a, so that's 4. The conjugate axes would be 2b, so 2 times b, which is 2. And what else could we be asked here? How does it open, I guess? It opens up and down because the y value is going to open like an upward, downward direction. What about the slope of the asymptotes? Well, I got to look under the y values. That's 2. If I square root that, it's 2. And underneath the x value, it's 1. So really the slope would be plus and minus 2, because you have a positive slope and a negative slope. And you could plug that into the equation above that we looked at. So anyways, I hope that covers everything that we've done in hyperbolas. I will do one more video after this that kind of talks about all four relationships together and how you predict which is which shape, basically. So I hope you guys are doing well, and we're almost done.